Okay, so we just learned what is a force, right? In summary, it's a push or a pull, and it can be on something, but it also has to be by something, right? That's very simple, and it's measured in newtons. It's a vector quantity. Now, how does it affect motion of objects? Okay, so let me give you another motivation to think about. Imagine you are in outer space. Well, let's say you can breathe, and you throw an apple, or let's say I throw this pen, right? I throw this pen forward, and after I let go, what happens to it, right? What happens to things? In outer space, I'll assume that there's no air resistance. It's far away. It doesn't collide with another alien or a planet. There's no other gravitational force. It's far away from every other planets or black holes or galaxies or anything. It's true vacuum, right? So if I toss, let's toss a bowling ball, right, forward like that. Right, sure. When I toss it, I'm applying some force on it. All right, that's good. But after I let go, I'm not touching it anymore. It's probably still moving. But my question to you is it moving faster? Will it start getting faster gradually? Sounds unlikely, but maybe. Or does it slow down, get slower eventually? Right? You start walking at a constant pace, at some point you get tired. Well, does it get tired? Or does it move on forever, right? Move in constant speed, right? So it maintains its speed forever and ever. What do you think? All right. So if you haven't already, put this in Piazza, and we'll see what the theory is. All right. So now, obviously, you can think intuitively what you might think. If you're on Earth, almost everyone, admit it, you would think things will slow down eventually, right? Is physics different on Earth than in the space? Does it follow a different law of physics, or does it follow the same law? Well, people used to think it's differently. Well, maybe in space, I can imagine things will go on forever, but on Earth, I think that everything without any forces, and now I need to be very clear, this is without any external forces, well, because if I start pushing it halfway through, of course it will get faster. If I start pushing it the other way, of course it will get slower, right? Let's not touch it, leave it on its own. And believe it or not, took ages of Greek philosophers who always thought that things will eventually slow down. There's a natural state, things want to slow down. And that has been the theory of motion for a long, long time, until Galileo came along and one of the first persons to disprove that theory. And it realized that's not the right answer. And what happens is things will always move in constant speed. This is the correct answer. Now, the footnote or the big asterisk over here is without external forces, right? So he was one of the first to understand that, yes, on Earth things slows down, right? If you roll a bowling ball, it will go on pretty well. It has a good amount of momentum, but eventually it will slow down. And that's not because it's trying to go to its natural state. The natural state is it wants to keep moving. The reason why it's slowing down is there's actually extra forces that slows it down. Okay, so that's one of the big discoveries. Sometimes it's a lot of time credited to Newton, but it's discovered before by Galileo, just a couple of years earlier. But Newton sort of put this and called it his first law of motion, right? And this is so important. Let's write this down. Before this, let me tell you, how did Galileo even think about this, right? And this he did what's called a thought experiment. What's a thought experiment? So I'm a theoretical physicist. So this is the most experiments I'll do. And so this is Galileo's thought experiment, right? So it's good to know why and how did he even come up with this, back then, a very radical idea. Think about this, right? So if you make a sort of a U-shaped kind of thing and you let a ball fall and sort of roll downhill like this and roll up to the other side. Now, if the surface is very, very rough, right? So you have a lot of friction and probably it'll just go sort of a little bit halfway and then roll back down. But if you reduce the friction, if you make it smoother and smoother, you can imagine in the ideal case, right? You can so this is something you can imagine being possible is the ball will go back up to the same height, like this, if it's completely frictionless, right? You can think of it as a certain amount of energy. Well, we haven't sort of defined that yet, but it'll sort of maintain its motion all the way through. Now, if you now make this side a little bit more slanted, like this, right? So this has a gentler slope. There's a very steep slope over here. What will happen? Will it go back? Well, you can actually try this out, but the answer is it'll actually go back to the same height, like this, okay? And now you can make a very, very gentle slope. I don't know, maybe this was 45 degrees, maybe this was reduced to 30 degrees, maybe this is 10 degrees now, right? And repeat this. Now, of course, if there's friction, the ball will probably stop somewhere, but if you can imagine the ideal scenario where you can make it as smooth as possible and you can have it go all the way back up to the other side. Now here's the question, right? So if I let this side to be completely flat and let go of a ball, and remember, no friction, what will happen? Well, what we've concluded is it always goes back to the same height. But if you make this completely flat, then it will just keep going forever and ever and ever and never stops. So with this thought, you'll realize that, hang on, if there's no friction, if there's nothing stopping it, it will keep going because it will never go back to the original height, right? And so this is one motivation, but yeah, we can formalize that, right? So. What we've learned is, the first thing we learn here is that we don't need a force to keep things in motion. In fact, what we do need is we need a force to slow things down. Okay, so this is what we learned. And we can summarize this into Newton's first law of motion. And Newton thought this is so important, right? He put this as his very first law in his book about how things move. If anyone knows Latin, you can check that out as well. So it says, without external forces, without a net external force. This is so important that you need to be able to recite this and memorize this in its entirety. And also I'll explain each little word for you so you understand it. Without a net external force, objects will either remain at rest or, so it can do two things. It either remains at rest or it will maintain constant velocity. Okay. So a bit long, but the gist of it, right? The emphasis is without a net external force. Well, we know what a force is. What is it again? It's a push or a pull, right? Without something pushing or pulling it back. All right, I'll explain what does net mean and external mean. Objects will either just remain at rest. It has an option. It either remains at rest or it maintains constant velocity. Well, it's not really an option. It depends on what it initially do. So let's put in some footnotes, right? So it remains at rest. In parentheses, it's if it was initially at rest. Right? So that means if something is staying there at rest, you don't give it any force. Imagine that something is floating in space, right? In outer space. If you don't touch it, it will stay at rest, or it will maintain constant velocity if it was initially moving. Okay, all right. So couple of words I'll explain. I'll explain what is net, what is external, and what does velocity mean. Okay. Just a quick tip about in your exams or future studying, you want to be able to. Don't have to recite it word for word, but the key points have to be here. And this is basically this is already most of the key points, right? So if you use different grammar or different wordings, but you need to be able to convey the point of this. But you don't need to write out the things in parentheses. That's sort of like fine prints, and it's fine if you omit it. If you need to reproduce this, someone in a test, if you are asked what is Newton's first law, the black parts are what you want to write, essentially, right? Okay, let's start with velocity, right? So you may have heard of that term before. If you don't know what that means, velocity, it contains two things. It means the speed and its direction, right? So that means if you don't have any net external forces, things will maintain the same speed and also the same direction, and that makes sense, right? It wouldn't suddenly just the banana that you throw wouldn't suddenly just turn around, so it won't change it. It will maintain its constant direction, the same direction, maintain the same speed, right? So velocity is the word that takes both of these into account. Now, does that remind you another thing of another concept? Right, exactly. That's a vector. So a velocity is also a vector quantity, something you can measure, and it has a magnitude and a direction. Well, the direction is the direction. The magnitude of this velocity is speed. Okay, we'll talk more about that in the future. All right, but that's what velocity is. You understand roughly what speed is, right? If you drive a car, you have speed. External force. First, let's explain external. It's because I could have something tied together. For example, I could have these two boxes tied together, and there's a string between them, or even a rubber band or a spring or whatever, right? Stick together. But external forces. So if I treat this as a system, right? A system is a collection of objects. An external force is something that affects the system as a whole. All right. So the spring that is sort of pulling the two together, that's internal forces, right? So if you have a spring that pulled them together, it won't affect its overall motion. If the whole system is at rest, then it will stay at rest, right? Or if the whole system is in constant velocity, it will stay in constant velocity. Okay, so that's what external means. You need sort of some external agent to push it. And net means the resultant, all right? The overall effect, okay? So this external means any forces from outside the system. Okay, so you see, if I consider this as a system, my hand pushing it, that would be from outside the system. The spring that is tying them together or pulling them together, yes, that's a pull, so that's a force, but it's inside the bubble that I'm considering, right? It's very subjective. What's a system? In this case, I'm considering this a system. If you consider them individually as a system, then the spring would be an external force, right? We'll get into more of that in the later on. And net just means the overall effect. Okay, because imagine if I'm pushing the system this way and someone else is pushing the system this way, and we push it with equal amount of force, but opposite in direction, then it won't move as well. So it doesn't mean that if you have an external force, it will move. It will start moving. You need a net force, right? So you need one side to be larger than the other. If there's some net like overall effect, one side wins, then you have the force. Okay, all right. So while we're at it, let's comment on how about what happens. So Newton's first law deals with something without an external force. What happens if you do have an external force? So let's talk about that in a separate video.